In this video, you will learn to use exponential and logarithmic functions to solve growth and decay problems. Now, when we talk about growth and decay problems, some examples of these would be, for example, compound interest or population growth. That would be exponential growth. Now, exponential decay, you have examples such as the value of a car, because it decreases over time, or in science, we have the half-life of radioactive substances. So each of these would be exponential growth or decay, meaning getting smaller. So we're going to look through each of these different examples in this lesson, beginning with compound interest. To illustrate this, let's say we had $10,000 invested at 6% interest compounded annually, and you were to find the principal after 4 years. So to illustrate this, we can find the value at the end of 1 year by taking the principal, so the amount that we started with, then adding in the interest that we earned. So the principal is going to be this entire amount, this 100% of the amount invested. So the principal is 100%. It is all of this. So that's 100% plus the interest earned is going to be 6% of that principal. So if you take 100% of the principal, add it with the 6% interest earned, the 6% of the principal, that gives you a total of 106% of the principal. So to calculate that, you can do 1.06 times the principal, so times 10,000. All right, and that's the process to determine the principal after 1 year. So we're adding the original amount with the interest earned, and when you do that, you see here in this table that we would have 10,000 times 1.06. So in this table we have the time in years, that's the first row, and then the second row is the principal in dollars. So 0 years right here, the principal is $10,000. That's our starting point. So after 1 year, we said is 10,000 times 1.06, right? You multiply the 10,000 times 1.06. And each year, you're going to have to multiply by 1.06. So we take this new principal, whatever this number is, we're not calculating at the moment, but whatever this is, we'd have to multiply again by 1.06 to get the new principal for year 2. Multiply by 1.06 again the third year and the fourth year to figure out our total at the end of 4 years. So notice when you keep multiplying by 1.06, we can write that more simply in math notation with exponents. So if you multiply by 1.06 4 times, by the end of year 4, we have 1.06 to the 4th power. Then that's times the 10,000. So our objective is not to get a final number answer, but to show you the idea of this process. All right, so in general, if you compound yearly, this is our formula. So A is the amount. So the amount is equal to the principal, the P, times 1 plus the interest rate to the T power. So R is the rate, T is time in years. All right, so this is our formula. And we see that because in this example, if we look at this number right here, after year 4, the 10,000, that's the principal. That's what we started with. The 1.06 is 1 plus the rate of 6% of 0.06. And the time in years is 4. That's the exponent. So that's where the T comes from in the formula. So we have generalized what we've done here to get this formula. Now the question is, what if it compounds differently? So instead of compounding yearly, what if it compounds maybe semi-annually or quarterly or monthly? So it's the same idea, but we have to account for the number of times it's compounded each year. So if we add to this formula n, which is the number of times compounded in a year, number of times compounded yearly, So if we use the letter n to represent that, where we would have to put that in the formula is both with the rate and then the time. So, for example, if the 6% was compounded, let's say quarterly, the rate that we need for each increment is going to be the 0.06 divided by 4. That's how much interest earned in 1 quarter. We divide by 4. So this number we have to divide by, that rate that we divide by, is going to be the number of times compounded. So quarterly, we divide by 4 because there's 4 different increments or payments. If it's compounded monthly, there's 12 different times compounded in a year. We divide by 12. So we have to divide this rate by n, the number of times compounded. All right, so that would take care of that. And then right here, the exponent is the total number of times you're multiplying. Okay, so if you are compounding quarterly, for example, after 4 years, okay, if we keep multiplying, it's going to be 4 years times 4 compoundings yearly. So 4 times 4, or 16, would be the exponent. So the exponent needs to be the number of times total that has been compounded. So it's the years times the number of times each year is compounded. So the formula, if compounded with any other increment, would look like that. And we see it here in the next slide, where we have the amount equals the principal times 1 plus the rate divided by n, raise that to the n times t power. So that is your formula, where again, a is the amount, p is the principal, r is the rate, t is the time in years, and n is the number of times compounded within a year. So let's take a look at an example of using this formula. Let's say a $15,000 investment is invested at 4% compounded quarterly. What is the investment worth after 20 years? So we can use the formula, and we see it typed up right here, and then we just plug in the numbers. So P, the principal, is going to be 15,000. The rate is 0.04, or 4%. That is your rate. Compounded quarterly, that means it's compounded 4 times in a year. So N would equal 4. So R is 0.04, N is 4, the principal is 15,000. And then the time would be 20 years. So time equals 20. So you plug all that into this equation. So we now have 15,000 times 1 plus R is 0.04, divide by n was 4, raise that to the n times t, or 4 times 20 power. So you're definitely going to want a calculator on this. All right, so here in the parentheses, 0.04 divided by 4 is 0.01. So you have 1 plus 0.01, or 1.01. 4 times 20 is 80, so your exponent is 80. And if you type into your calculator 1.01 to the 80th power, you're going to get 2.2167, etc. So you take that number, multiply by 15,000, and that gives you your final answer, which would be $33,250.73. So that is the amount that your investment would be worth after 20 years. So that's assuming you're not putting any more money in, and assuming the interest rate stays the same. All right, notice, so after 20 years with that rate, you have more than doubled your original money. Let's take a look at another compound interest problem. Example 2 says a $2,000 investment is invested at 8% compounded quarterly. And the question is, when will the investment double in value? So this is actually asking for something different. This is asking for a time. So time is your unknown, but you're still going to use the same formula. It's a compound interest problem. So the question is, what do you plug in, and then how do you solve for t, for time? All right, so the principal is $2,000. All right, so the principal is $2,000. So that's the amount you're investing. It's invested at 8%, so the rate is 8%, so or 0.08, compounded quarterly. Quarterly means is compounding 4 times within a year. So N is going to be 4. All right, T is unknown. That's what we're trying to find. So then A, the amount at the end, is going to be doubled. So the principal is being doubled, which means the amount at the end is going to be $4,000. So you plug all that into this formula. So you have 4,000 for A equals P, 2,000, times 1 plus R, 0.08, divided by N, or 4. Raise that to the N times T, or 4 times T power. Now, we need to then take this, simplify the parentheses, and then try to solve for T. So to simplify the parentheses, we have 0.08 divided by 4, which is 0.02. And 1 plus 0.02 is 1.02. So we now have 2,000 times 1.02 to the 4t power. So from here, we're trying to solve for t, so we can get rid of this 2,000 being multiplied. We can get rid of that by dividing both sides by 2,000. So when you divide both sides by 2,000, it cancels. We now have 2 on the left equals 1.0t, or 1.02 to the 4t power. All right, so now from here, this is when we can use logarithms, as we've learned in a previous lesson, because we have a variable in the exponent. And that's when logarithms can come in handy. Okay, we can use logarithms to get the exponent out. All right, so what we can do is we can rewrite this as a logarithm. So we can rewrite this as log base. The base is 1.02. And then it's going to be of 2 equals 4t. So the base is 1.02. A log is or equals the exponent, so it's equal to 4t. And now from here, we can figure out what is log base 1.02 of 2 equal. So many calculators at the time that this video is being created will not do that unless you have a fancy calculator. But if you don't, you're going to have to convert into a base 10, which your calculator should be able to do. So to convert to a base 10, we can use our change of base formula, where we take log base 10 of the 2, divide by the log base 10 of 1.02. So we see that right here. So assuming you know how to use your calculator to type in log of 2, you type in log of 2, you get this decimal on the top, 0.3010, etc. And then log of 1.02, you get 0.0086, etc. And when you divide those two numbers, you get 35.00. All right, and then from here, we can solve for t by dividing both sides by 4. So t would be 35 divided by 4, which gives you 8.75 years. So at this rate, your investment would double in 8.75 years. So by the way, just a real life application of this, it's very important to invest because you see here, your money is working for you. If you invest it and have a good interest rate, you can double your money, in this case, after 8.75 years. So it's good to be on the investing end as opposed to being in debt and having to pay that interest rate. All right, so this is one application, is with compound interest. Another application of exponential growth or decay is with population growth. So population growth is exponential in nature, by nature. So for example, these are actual numbers, by the way, where in the entire world, in 1927, the population was 2 billion. In 2018, the population is 7.616 billion. Now our objective is we want to try to find the rate of our growth, and we're going to try to use that rate of growth to predict the population in 2050. Okay, so I guess we're assuming that the rate of growth is going to remain the same, which is in real life not necessarily a fair assumption, but for our purposes we're going to assume the rate will be pretty much a steady rate. All right, so what we want to do to realize this is we're going to kind of use the same idea as we did with the compounding interest. All right, so to figure out some amount, we realize we're going to start with, I guess with the compound interest was a principal. Here it's going to be population. And then you do 1 plus r to the t power. This was for compounding interest, but the idea works as well for population growth as well. So same logic. Okay, we're going to start with a population. So the population is 2, or 2 billion. That's what you're starting with. The ending amount is going to be 7.616. That's what we ended with in 2018. And then you do 1 plus r to the t power. T is time in years. So how many years transpired between 1927 and 2018? Well, 1927 to 2000, that's going to be 73 years, plus 81, or plus 18, sorry, it's going to give you 91 for the number of years. So between these 2 years of 1927 and 2018 was 91 years. So what we can do is we can use this little formula, this little equation, to try to solve for r, figure out what is the rate. So we see that typed up right here in the notes. All right, so to solve for the rate, we want to get r by itself. So you can work in reverse order of operations. So order of operations, we have parentheses, exponents, multiply, divide, add, subtract. Working in reverse, we would do the multiplication of the 2 first by dividing. So we divide both sides by 2. We have 3.808 on the left. So we have no addition, subtraction. We've done multiplication and division. Next we have the exponent. Okay, so we have exponents in parentheses remaining. So using the exponent, we want to get rid of the 91st power. So the opposite of raising to the 91st power is taking the 91st root. So it seems like a kind of a crazy thing to do, such a large number, but that's what you're going to do. You're going to take the 91st root of both sides. When you do that, on the right side, the 91 exponent cancels out. On the left side, you have the 91st root of 3.808. Now remember that this radical you can write with exponents. So your calculator maybe can do this directly. If not, you could convert to an exponent, and that would give you 3.808 to the 1 over 91 power. And then if you type that into your calculator, you're going to get 1.0148, etc. And this decimal keeps going. So that's equal to 1 plus r. So to solve for r, we can subtract 1 from both sides, and that would give you r equaling 0.0148, which, if you convert to a percent, move the decimal point 2 places to the right, you're going to get 1.48%, which you can round to 1.5%. So the rate of increase is 1.5%. So now we found the rate of increase. Now the question is, how can we use this to predict the population in the year 2050? So realize that we're going to take the 7.616 in 2018, and we're going to keep multiplying by the 1 plus r. So this rate of 1.5%, add that with 100% of what we started with, so 100% of the population. So if you add that together, 1 plus r, 1 plus 1.5, this would be, by the way, decimal is 0.015. So 1 plus 0.015 is going to be 1.015. All right, so that is going to be the amount we multiply by each year. So each year, you multiply by 1.015 to get the following year. Okay, that's the 100% of the population plus the additional 1.5% increase. All right, so that's what you're going to do. You're going to take the 1.015 and you're going to keep multiplying 32 times because it's going to be 32 years between 2018 and 2050. So the exponent is 32. All right, so that's the idea of what we're trying to do. So we, again, can use the formula where the amount at the end of, by the end of 2050 equals the original number, original population, times the 1 plus r to the n power. All right, so the original population we're starting with is 7.616. We're starting with that. That's going to be your p. And then 1 plus r, we already basically did that right here. 1 plus r is 1.015. Raise it to the n power, that's going to be 32. So that right there is going to be this part, the 1 plus r to the n power. So we take 7.616 times 1.015 to the 32nd power. So if you type that into your calculator, 1.015 to the 32nd power, you should get 1.6103. And then multiply that by the 7.616, and that's going to give you 12.26, and that's going to be billion. So based off our calculation here, with this information, by 2050, we can predict maybe around 12.26 billion. Now again, this prediction is assuming that this rate is staying a constant, which in reality, that rate would change maybe over time. You know, there's years maybe when, you know, fewer people are passing away, or maybe more births within a year. So I mean, there's variables that can affect that rate, but assuming a constant rate, this could be our prediction. Next, we're going to talk about a doubling growth formula. So the formula I'm going to show you, and then we'll kind of explain how we got there. So here's the formula. We have n equals n sub o, or 0, times 2 to the t over d power. So what does all this mean? Well, n is the number, or population, so it's the amount at the end, okay, equals n sub o, or 0. That's going to be the original number, or original population. The t is time, and the d is the doubling rate. So the doubling rate is how often it is doubling. So where does this come from, and how can we use it? Well, where it comes from is if you were to think of an actual example. Let's say the growth rate of 1.4% per year will approximately double the population every 50 years. Okay, so assuming that's a true statement, okay, we can use this information. So if you think through to figure out the amount at the end of a certain period of time, the number of population at the end, what we do is we start with the original population, and then we keep multiplying by, it's going to be 1 plus r. So 1 plus r, so it's going to be 100% plus this rate, which is 0.014, and then raise that to the t power. Okay, so it's basically like the principal formula, where the compounding interest formula, where you do a equals p times 1 plus r to the t power. We're just kind of using different letters at the moment. So the n sub o is like your principal, n is like your amount. And if we think through this, where we plug in numbers, so let's say we plug in, so r is 0.014. We have 1 plus 0.014, or 1.014. To the t power, this is time. Time is 50. Let's put a 50 right there. That's equal to n. So we see that typed up right here. Okay, so what we're wanting is we want the population to double. It says the population will double. So meaning this original amount, the n sub o, we're going to double that. So this n becomes really double, so 2 times n sub o. So we have here, if we want, we can rearrange this, put the left side on the right side on the left. Doesn't matter how we write this. But we have n sub o times 1.014 to the 50th power equals 2 times n sub o. All right, so then if we rearrange this, we can divide both sides by n sub o, and that's going to cancel out over here on both sides. We're left with 1.014 to the 50th power equals 2. Now if we want to, we can get the 1.014 by itself by getting rid of this 50th power. Well, how do you get rid of the 50th power? Well, you take the 50th root of both sides. All right, so when you do that, the root and the exponent will cancel. You're left with 1.014 equals the 50th root of 2. Now remember, we can write exponents, write radicals as an exponent, where we can write this as 1 over 50. So the exponent with the 2 is going to be our numerator, and then the index, the 50, is your denominator. So we can rewrite this as 1.014 equals 2 to the 1 over 50th power. So how is this helping us? Well, if you take a look here at this first line, we said 1.014 is equal to 2 to the 1 over 50th power. So we can replace this 1.014, replace that with the 2 to the 1 over 50th power. So now we have n equals n sub o times 2 to the 1 over 50th power to the t power. So I guess we should show that here for you. So the 1.014 is raised to the t power, but you're replacing the 1.014 with 2 over 1 to the 50th. So that is raised now to the t power. So you have a power to a power, you multiply the exponents. 1 over 50 times t would give you t over 50 as your exponent. And that's where this comes from right here. All right. So now, notice what we have. We're trying to generalize this. And we see here the 50, that is the doubling rate. It's doubling every 50 years. The 50 is your doubling rate. So that's where the d comes from in this formula. So notice the similarity between this and this. So the d, the doubling rate, is 50 in this particular example, and that's where this general formula comes from. And what's probably a more simple approach of viewing this formula is we realize to double something, we're going to have to keep multiplying by 2 over and over again, right? So that's the idea as well here in the formula, where you take the original number, so n sub o, the original number, multiply by 2 to some power, multiply by 2 over and over again. And the power is determined by how many times it's going to be doubling. All right, so for example, if it's doubling every 50 years, if the time is 50, it's going to double 50 over 50, or 1 time, right? 2 to the first power, it's going to be multiplied by 2. If it's been 100 years, then realize that it's going to be doubling twice, right? Because it doubles every 50 years, so it's going to double twice. So it'd be 100 over 50 for your exponent, which would be 2, right? Because it's going to be doubled twice, so 2 to the second power. So that can keep going. If it's 150 years that has gone by, the number of times it's doubled would be 3. 150, the time, divided by 50, the doubling rate. So that's kind of the idea of the exponent. And that's where the formula, you can maybe think of the formula coming from there as well. Original number times 2 over and over again. So this side work over here basically just verified what we've done over here. So this is conceptually what we're doing, and over here verifies mathematically that this is the correct formula. Now the question is, how does this work? How do you apply this to anything that's actually practical? So where this comes into play is if you are dealing with maybe bacteria, for example. Because bacteria you can sometimes measure it, or you can talk about how fast it doubles. So I'm not a science person, but this is one application, and you can see this maybe in different science fields. But what we can do here is we see that a certain bacteria population doubles in size every 36 hours. And the question here is, by how much will it grow in 5 days? So what we do is we take this formula. We take n equals n sub o times 2 to the t over d power. Where again, here's your key. So this is what everything means. And we plug in what we know. All right, so we know the time. The time is 5 days. Now 5 days, convert that to hours. We do 5 times 24 to get 120 hours. So time would be 120. We're dealing in hours here. Because the doubling size, d, would be 36 hours. So because this is in hours, we want everything else to be in hours as well. So d is 36. All right, and that's really all we know. So we plug this in. So we have n equals n sub o times 2 to the t over d power. We have 120 over 36. Well, what is 120 over 36? That is 3 1/3, or 3.3 repeating. So our exponent is 3 1/3. So now we raise 2 to the 3 1/3 power, and you can type that in your calculator, and you're going to get 10.079. So if we put the 10.079 first, rearrange this, we would have n equals 10.079 times n sub o. So what does this tell us? This tells us that in 5 days, the amount of bacteria that we have, n, the population of the bacteria, will be 10.079 times the original amount, n sub o. So we can say that whatever the population was originally, in 5 days it's going to be 10.079 times larger. So the population increases basically by tenfold, so 10 times the original amount. So this is one application of the doubling growth formula. And then if you had the original amount, the n sub o, we can figure out the actual number, the actual population at the end. Next, we're going to switch gears and talk for a moment about exponential decay. So what if numbers are getting smaller? So we've, up to this point, just dealt with the exponential growth. So one example of exponential decay, as mentioned at the beginning of this video, is the value of a vehicle. So the value of a vehicle, if you buy it right off the lot, will decrease in value a certain amount every year. All right, so let's say we bought a $30,000 car and it loses 10% of its value each year. What is the value after 5 years? So this is really the same idea as compounding interest. We can use different letters in the formula, but it's all the same thing, where the compound interest formula was a equals p times 1 plus r to the t power. All right, same idea, but instead of adding an interest rate or a rate of some sort, in this case it's decaying, which means we're subtracting some rate. So we start with some original amount, the principal or whatever we're dealing with, and we're subtracting 100% minus a certain rate each year. And each year it does that, we keep multiplying by that for a certain number of years. So t is your time. So it's basically the compound interest formula, but we can use different letters to represent this. So using the same letters as the last example, we can use n for the final amount, n sub o is the original number, and then we have 1 minus r to the t power. So it's all the same thing, just different notation. So just know how to use this. So using this formula, we can figure out the amount, the value after 5 years. So you plug in n sub o, the original amount. So we'll plug in 30,000. That's n sub o. And then the rate is 10%. That's the rate of decay. So 0.1 is 10%. And the time is 5, so 5 years. Plug all that in, we now have n equals 30,000 times 1 minus 0.1 to the 5th power. 1 minus 0.1 is 0.9. 0.9 to the 5th power, you can put into your calculator. You're going to get 0.59049. Multiply that by 30,000, and we get $17,714.70. So that's kind of crazy if you look at the actual numbers here. The value is basically half of what it was 5 years before. All right, so I'm not sure the actual the rate of decay for vehicles, but it's probably something close to this in all reality. All right, so here, just know how to plug in the numbers to get the answer that you want. Now to finish off, one other example of exponential decay is half-life. Where this comes into play is with radioactive material. So the half-life, by definition, is the time it takes until half of the original substance remains. All right, so for example, if the half-life is 400 years, that means after 400 years, you now have half of the amount of substance that you started with. All right, and our formula for this is basically the same idea as the doubling formula. So the doubling formula, remember, was n equals n sub o times 2 to the t over d power. All right, that's your doubling formula. So the 2 is the idea of doubling. So here for the half-life, we don't want to find when it doubles, we want to figure out when is it half. So we take the original amount, times that by 1/2, and then it's going to be t over, instead of d, we use the letter h for half-life. So instead of the doubling rate, it's the halving rate. When will it be half? So it's really the same formula, except instead of 2, we have 1/2. Instead of doubling, it's going to be a half-life. So this is your formula, n equals n sub o times 1/2 to the t over h power. And here is the key on the side. All right, so let's take a look at one example. For this example, we are told that the half-life of radium is 1600 years. How much of a 10 milligram sample will remain after 3000 years? So for this, you plug in the numbers. The 1600 years, this is your half-life. This is h. 10.0 milligrams, that's the original number, the original amount. So we have n sub o. And then how much will remain after 3000 years? 3000 years, that's your time. So you plug all that into your formula. So instead of n sub o, we have 10. Instead of t, we have 3000. Instead of h, we have 1600. So that's what you plug in. So make sure you follow order of operations. We don't multiply until we take care of the exponent. So if we do 1/2 to the 3000 over 1600 power, type that in your calculator, you're going to get 0.272627, etc. Multiply that by 10, that moves a decimal point over one place. You're going to get 2.72627, which would round to give you 2.7 milligrams. So the answer is after 3000 years, you have 2.7 milligrams remaining. And so we've seen the different formulas in this lesson for compounding interest, for population growth, for exponential decay, for the devaluing or depreciation of a vehicle. And for all of these different formulas, okay, if you understand the formula, you understand what everything means and when to use it, you can, at times as well, figure out different things. So in this case, we're trying to find n, but there's times, you could find out what is t or what is h or what is the original amount. So if you understand how to plug in the numbers correctly and then how to solve these different types of equations, then you can solve for any unknown part. And this concludes our lesson for today. We will see you next time.